so much for inviting me, and sorry for the inconveniences caused now. My name is Michael Schmitt, as announced already, and I'm the head of the Earth Observation Lab at the University of the Bundeswehr in Munich. It's a bit of a weird name for a university. Bundeswehr is basically the name of the German military. So we are a classic university with classic bachelor's and master's degrees. But we are basically fully owned by the German Ministry of Defense, and all of our students are soldiers of the German military. But our research is not only military affiliated, oriented. We are totally free in our research and in our teaching. So it's a bit of a hybrid situation, which is, as I find personally, quite inspiring. And today I'm going to talk about deep learning for SAR image analysis. And in this talk, I will first give a very quick introduction to deep learning in remote sensing. So of course, I'm talking now to people from the EO Data Science Lab who all know very well what remote sensing is and how deep learning is applied to these talks. But I've heard that there could also be people from the general computer science field. So maybe to bring everybody on the same page, I will lose a couple of words on that topic. Then I will dive in a bit deeper into my main field of specialization, which is SAR image analysis, and I will talk a little bit about the peculiarities of SAR data. And then I have brought two different, let's say, examples from my research, which is a solution under the umbrella of hybrid modeling. So how can we pair domain expertise with a deep learning based modeling to solve interesting issues? And then I bring what I personally deem the highlight, which is parameter awareness in SAR-specific deep learning models. So let's get right into it with the introduction to deep learning in remote sensing. I've summarized the topic a little bit a few years ago, and basically what you see here in the upper left is the number of papers that have either the keyword machine learning or the keyword deep learning together with keywords such as remote sensing or Earth observation somewhere in them, in the keywords, in the title, in the abstract or whatever. And what we see here is basically that the pairing of remote sensing and machine learning started already more than 30 years ago in 1991. So it's almost an ancient topic in remote sensing, actually. And then from 2008 on, we had the first papers that addressed some sort of deep learning and remote sensing. And then if we compare both lines, both of them are massively and almost exponentially on the rise. But from around 2018 on, deep learning actually took over and is now more prevalent in remote sensing than classic machine learning. And that, of course, is something we all know, and that's also why labs such as EO Data Science labs exist, because deep learning is everywhere these days in remote sensing, and this can also be seen in the many review papers that already exist on the topic. There are so many review papers on deep learning in remote sensing that I believe we soon need a review of review papers. So it's really an abundance here. And what are we actually doing if we apply deep learning to remote sensing data? Well, actually, I want to make the bold statement that quite many applications have a similar target in common. So we very often have as input an image and as output, again, an image of the same resolution or image-like data, let's say. So the most prominent example certainly is what's shown here in the upper two figures. And that is semantic segmentation for land cover classification. I mean, this is as old as remote sensing itself, pretty much, land cover classification. You put in an image, and the output you desire is a land cover map of ideally the same resolution. And this, of course, is something you can very well model with deep learning as well. And the second example here is a bit more innovative, maybe, and this would be image-to-image translation. So the idea here is you put in, for example, a SAR image, and your desired outcome is something like an optical image, which is a bit easier to interpret for laypersons, for example. I mean, this is not every problem in remote sensing. Deep learning is like that. There's also scene classification, for example, or other tasks, but many tasks are exactly like that. also, for example, pixel-wise biomass estimation or forest height retrieval or other things, soil moisture estimation. All of these things you put in an image and you want to get out raster data or image-like results. Now the question is, if this is the main topic, the main task, could there be one model to train them all? And you could come to believe that because there are so many papers out there that use UNet variance. Yeah, I mean, everybody knows the UNet. The UNet original article has been cited more than 100,000 times by now, probably even more. So you have to update this slide pretty much every month. And if you look at the remote sensing literature, the UNet really has to become the go-to standard for many applications, from land cover classification to biophysical parameter regression and so on. I've scraped from a Google search a couple of nice illustrations of UNet variance, but of course there are endless more. However, you have guessed it. The rest of the talk will be about the fact that I don't believe that the UNet is the end of deep learning applied to remote sensing, the end of EO data science. I believe there's much more to it, and I want to use SAR to illustrate why I believe this is the case. And for that, I want to start now explaining a few peculiarities of SAR data. So I don't know how familiar you guys are with SAR, but the entry statement I want to make is that SAR data analysis is not the same thing as classic image analysis. Typically, we have a radar antenna mounted on some flying platform. It can be a drone, it can be an aircraft, it can be a satellite, and this platform is moving, and during the movement, pulses at a high pulse repetition frequency are sent to the Earth, and then their reflections are collected at the radar again. And during the movement, a so-called synthetic aperture is created, which allows high-resolution imaging independent of the distance to the target, and is allowing us to create images from these radar pulses. And this is massively different to any electro-optical imaging because, for example, we do not passively collect reflected sunlight, but we actively illuminate the scene with microwaves and collect the reflections of that, the backscatter. We don't count photons, but we record amplitude and phase of the received signal, so we end up with complex valued measurements eventually. We don't have a near-nadir viewing geometry, but an oblique observation geometry, so we always observe the scene in a non-optimal fashion, let's say. And finally, we don't have angles as primary measurements, but range measurements. And so everything is really massively different than in optical imaging, even though we end up with images that might look a little bit similar to grayscale optical images. And the fact that we have this let's say, strange imaging gives us some peculiarities of SAR images, and they are first and foremost radiometric. So if we look here at complex valued SAR observations, we can split them into an amplitude image, which is shown in the foreground here, and also in a phase image, which is shown here in the background. And if we look at a homogeneous area here, for example, then we see that we have, even in a homogeneous area, we have some sort of noise-like appearance. So not all the pixels have the same gray value, but there are some bright pixels and some dark pixels. And if you look at the statistics of that, we see that we end up with non-Gaussian statistics. In this case here, it's resembling a Rayleigh distribution. So it's the first thing we see is we have non-Gaussian statistics in the amplitude imagery. And then in the background here, this is the phase of the single image, and this actually follows a uniform distribution. So this phase alone is pretty useless. Together, phase and amplitude provide the complex signal we have to deal with if we want to exploit the full information. Even more critical probably are the geometric peculiarities of SAR images, which come from the fact that we have this aforementioned oblique viewing geometry and the fact that we don't have an angular measurement system, but a range-based measurement system. Because this leads to the fact that we see two different imaging effects. One is called layover, that has elevated objects collapse towards the sensor, and shadowing, which means that the radar cannot observe the area behind elevated objects. Yeah? Both of these effects are seen here in the sketch in the center of the slide, but also in the two example images on the left here and on the right. The thing that also the slide seeks to address is that these effects are highly dependent on the local incidence angle, so on the actual observation geometry. So the greater this theta is, this off-nadir angle, the longer is the shadow behind the building and the shorter is the layover in front of the building. So in other words, the shorter is the appearance of the collapsed buildings here in the amplitude image, and vice versa. So basically the smaller this off-nadir angle theta, the longer the layover, the longer appear the buildings and the smaller the shadowing. So takeaway message from the slide: the appearance of objects, especially in urban environments and in very high resolution data, is heavily dependent on the acquisition geometry. To summarize, many remote sensing tasks can indeed be tackled with deep learning, and we have an abundance of literature, an abundance of new business models, and an abundance of very cool new scientific results. The unit is a very popular and powerful choice for many of these tasks, especially segmentation and regression, pixel-wise regression. But we also learned that SAR data are not images, but complex measurements with physical meaning. And therefore, I hypothesize, or I claim, that SAR expertise must be combined with modern deep learning approaches for the best results. And as I said, I have brought two examples, one from hybrid modeling and then one from parameter awareness in SAR-specific models. Let's start with the hybrid modeling case, and here we apply this to the simulation of complex valued in-SAR data. The background here is there is some need to simulate realistic SAR or interferometric SAR data, mostly because SAR images are sometimes quite difficult to interpret, sometimes quite difficult to understand, and simulation can help to understand these images. And there's, of course, an abundance of simulator solutions existing already, but many of them show certain limitations. So many of them simulate, for example, only amplitude or intensity, like here shown on the right, the famous RAY-SAR simulator of Stefan Auer of the German Aerospace Center. I mean, it's not even amplitude and intensity, it's something related to that, but it's not a realistic SAR image in the radiometric sense. Then many simulators need a highly detailed 3D model as input, like a CAD model, for example, which is often not available. And many simulators have a very high computational demand due to the need for detailed ray tracing. And all of that is not optimal. So we thought a couple of years ago, can't we come up with a deep learning based solution for the simulation to speed up the process and to make realistic data that is also realistic in a radiometric sense, for example. And then we developed over the years a multitask network for complex valued in-SAR data simulation. And here the main problem is that the processing of complex valued numbers is not a straightforward thing in deep neural networks. So many people use standard solutions where they just split the data into real and imaginary parts and pass these through the network. But we believe this is not really taking along the full information, also because the correlation between real and imaginary part is lost. So we thought we want to go a different way. We want to convert the complex valued in-SAR measurements into interpretable real valued variables. Yeah, and then we finally can model everything in a hybrid way, combining domain expertise and a deep neural network to solve the issue. And now, without going into too much detail, let me guide you through what we did here. So the basis for everything is the age-old Goodman's model. Probably everybody knows who is working with coherent imaging data, such as in-SAR data. And that basically says you can split the complex interferometric measurement into the product of the two amplitudes of the input images, the coherence magnitude of the input images, and the complex phase difference between the two input images. So eventually you end up with 4 real valued quantities. And if you hypothesize that the two amplitudes U1 and U2 are similar because they show the same scene, then actually you have 3 real valued quantities, the reflectivity, the coherence magnitude, and the interferometric phase difference. And this is exactly what we did here. So we split the complex valued numbers into 3 interpretable real valued physically meaningful components, which we can easily model in a multitask network to have them predicted. The second thing is, because we found that the model has a hard time learning the influence of temporal decorrelation. So what happens if you put in data with different temporal baselines? And therefore we added a hybrid coherence decay model based on expert knowledge from the field of SAR interferometry, and have an exponential decay for pixel-wise interpolation of the coherence decay. That just makes the coherence prediction more realistic. And then finally we added back here a parameterized renoising model that captures both speckle and noise, and its parameters are optimized to reproduce circular Gaussian scattering behavior, but can theoretically also be extended to heterogeneous or non-Gaussian scattering regimes. And we added that because we found that the deep learning model has a very hard time simulating realistic speckle. We basically always got noise-free SAR images as a simulation result, but we actually wanted noisy images as a result to make them more realistic. And therefore we added this model. So you see that is a mixture of a deep neural network that takes the complicated task of image simulation, image-like data simulation, but then we pair it with expertise from SAR textbooks and in-SAR textbooks to really create realistic data eventually. And this is why I call this hybrid modeling. We did a few experiments in a proof of concept fashion here. And for that, we basically extended the GeoNRW dataset that was published earlier by a third party with interferometric data. And what the dataset eventually has is a LiDAR-based digital elevation model and land cover maps, both at 1 meter spatial resolution, showing urban and semi-urban areas in North Rhine-Westphalia. And we used from this dataset 2 subset cities, namely Dortmund and Hagen. And we extended them with co-SSC interferograms acquired by the German Tandem X mission, acquired in strip map mode with approximately 3 meter spatial resolution. We took the reflectivities from the singular complex magnitudes and estimated phase and coherence by one of the most established filters, the FINET. And with that, we created 542 overall patches, which we split randomly in a 95.5% way. So you see, this is not what I typically advocate, a spatial holdout set and large data set and so on, because here we first wanted to show a proof of concept that the whole idea of the hybrid modeling works at all. And to show you an example, this is the SAR image of Dortmund taken from the Tandem X co-SSC amplitude. And this is our simulated amplitude. And of course, maybe the bandwidth, the dynamic bandwidth or dynamic range of our simulation is not as good. There's a little less bright scatterers. This is because we are working here with the circular Gaussian assumption and not with deterministic bright scatterers. But overall, I think we have simulated a really realistically looking SAR image only from a digital elevation model and a land cover map as input. This is the target, let's say, coherence, which is again a product of estimation because there is never ground truth coherence. So we have to take this with a grain of salt. And this is our simulated coherence. Yes, there are differences in the details, but the overall agreement between the whiter parts and the darker parts, I think, is quite well given. So we are going in the right direction, especially if we have in mind that there is no ground truth for coherence. And then finally, this is the interferometric phase between the two acquisitions, and this is the simulated phase. There are a few artifacts left, but overall, it's also going into the right direction. So to summarize this first approach, which is still work in progress and only a proof of concept, I wanted to show that the combination of deep neural networks and domain-specific model elements allows the modeling also of complex relationships And the integration of multitask learning and hybrid modeling acts as a regularizer so that the model can be successfully trained even with a low number of training samples. This is like for all physics-aware machine learning or deep learning models. The physics kind of act as a regularizer and you need less data. But again, this is research still in progress, and future work will also have to involve larger data sets, of course. Now, let's come to the second use case I've brought along, and this is parameter awareness in SAR-specific models. And here the use case is height reconstruction from single SAR intensity images. To again motivate the research a little bit and bring everybody on the same page, what we are talking about here is basically inspired by single image depth estimating from general computer vision, a hot topic for years in robotics, autonomous driving, etc. Because if you can estimate depth perception from a single image, this is a great thing because it mitigates the need for stereo cameras, for example, and can be very cool to speed up things and or to get initial guess data, approximations, and so on. In remote sensing, people started quickly to adopt the strategy of single image depth estimation and converted it to single image height estimation. Here, the target is not depth, so something measured relative to the sensor, but height, so something with respect to some invisible geodetic reference. So I'm a geodesist by training. I could now give you a 90-minute lecture at least about height references and about how to model heights, etc. I will spare you that, but believe me, predicting height is much more difficult than depth. And generally, of course, both depth or height estimation from a single image are ill-posed problems. Because you want to infer the 3D environment from a two-dimensional image. So it's generally a challenging topic, but something that is well controlled by now. We have started to work on the whole thing in 2021, and in 2022, we managed to publish our first paper about it in the ISPRS journal, which was basically only the proof of concept, not really calibrated heights were predicted yet. And what we used was a fairly standard unit. So coming back to what I said in the beginning, with units, you can solve almost everything, right? Then in 2024, we were finally capable of publishing, let's say, a fully fledged framework that you can really use and produce data with. It was so successful that we eventually also licensed it to Airbus Defence and Space, so to industry. And here we used a unit with a metadata infusion block eventually. So a way to embed meta information into the unit. In the same year, we published SAR to height dual, which is an extension of the SAR to height model. And just allows in a second input branch a second image of the opposing viewing direction to get a more comprehensive reconstruction. So it's basically a unit with the same metadata infusion block and two input branches. And our latest publication, published in early 2025 on the Earth Vision workshop in the frame of the CVPR, is the so-called SAR-former, which is a vision transformer with parameter tokens. And this last model, our, let's say, highlight is the model I want to present you today, because I believe it's an excellent example for a parameter-aware deep learning model that understands sort of how SAR works. Basically what we did here, early work showed that unit-based architectures can be used to reconstruct urban height maps. We were basically already happy. But we also found, and this is what I said in the introduction, that SAR observations of urban areas heavily depend on acquisition mode and resolution, on observation angles such as azimuth angle or incidence angle, sensor calibration, and other things. And if you really want to create a powerful model that can also really be used in practice, in practical applications in industry, so to speak, then you would need a huge diversity of large data sets to capture all possibilities of the real world. And because that's not possible alone due to costs, we thought, let's use a vision transformer with metadata tokens and self-supervised pre-training to tackle the issue and to get a robust and good model, effective model, even with less training data available, or let's say at least less labeled training data. So this brought us to the SAR former. And as mentioned, this is a vision transformer specifically tailored to SAR with multiple inputs and multiple outputs. And I can guide you really quickly through its inner workings on this slide here. You see that the SAR former accepts n SAR images with arbitrary angles. In this slide example here, the n is equal to 2. So here it accepts 2 images, and they can have different imaging modes, different incidence angles, different azimuth angles. They can be fully independent and arbitrary, so to speak. In this case here, we see the left image is a strip map image with an off-nadir angle of 43 degrees and an azimuth angle of 280 degrees. And the second image is a staring spotlight image with an off-nadir angle of 35 degrees and an azimuth angle of 80 degrees. And the fact that the azimuth angle is a little more than 180 degrees different means that the satellites flew into opposing directions. And this means here the layover effect I've mentioned earlier leads to the fact that the Eiffel Tower in Paris here falls towards the east in the left image and towards the west in the right image. So both images don't really fit to each other. And if you use standard approaches, you won't get a nice and decent result. And then the images are passed through the SAR former together with metadata information. So we provide the variables m, theta, and az. And m stands for the imaging mode, spotlight or strip map. Theta is the angle, and az is also the angle, the azimuth angle, which are passed as scalars into the vision transformer. And then we have a number of outputs. In this case, it's 4 outputs. It's a height map in the original radar image geometry. So basically every pixel is converted into a height above ground for every view. But additionally, and this is even more interesting, or what we really want, we get the heights already corrected to a map geometry. So in an actual top view, if you wish, and additionally building a building footprint mask, a binarized building footprint mask also in a top view. And if you combine then the building footprint mask with the height map and render the whole thing, you can end up with a 3D city reconstruction like shown here on the right. This is a more detailed view of the SAR former architecture, and it also illustrates what is typical for vision transformers, namely that you have a pre-training phase that is reliant on a masked autoencoder pre-training, and you have a fine-tuning phase later where you really need labeled data. I won't go into detail here now because I think vision transformers are well established by now. But what makes our, let's say, SAR former special is what you see here as the T1 meter and T2 meter, which is basically the meta data tokens that are created by the so-called APE module, and APE stands for acquisition parameter encoding. So basically here, this APE module takes the 3 scalar values I've mentioned earlier and converts them into metadata tokens, which are then passed through the network together with the image tokens. Yeah, and this makes the model understand better what it's really observing currently, and why these images look different. And this helps a lot in the masking. I will say something to this in a second. And later in the fine-tuning stage, you basically add 4 heads, or 3 heads if you want, one for the heights in slant range prediction, one for the heights in top view prediction, and one for the building footprints in top view prediction. We created a large data set to train this model. It's currently based on almost 900 very high resolution SAR images from different missions. Most of our data, so almost 400 images, come from Umbra, the American company with the huge open data program. Then some good 300 images from the TerraSAR-X mission, which we got over a research proposal from the German Aerospace Center. Then a bit more than 150 images from Capella, also via the open data program. And then because one of my former PhD candidates works for ICEYE, I was also capable of getting my hands on a couple of ICEYE images. These images were acquired in 2 different acquisition modes, namely the spotlight variants of the missions and strip map. The incidence angles range from 12 to 78 degrees, and there's some diversity in terms of spatial resolution. So the strip map images all come at 3 meters, but the spotlight images come from a couple of centimeters to 2 meters. So there's some variety. But what's most interesting here is that we use data of 125 global cities. And only for 26 of these cities, we actually have ground truth labels, which in our case for height reconstruction is LiDAR based. So here really we have the strong and urgent need to do self-supervised pre-training, because with this low number of labels, we have a bit of a problem. Yeah, so what did we do in the pre-training? Yeah, as I said, we used the standard masked autoencoder, but the nice thing is, due to the acquisition parameter encoding, we can play around a little bit with the masking. So instead of just using the classic random masking as shown down here, where individual tokens are masked and the model is asked to reconstruct them, we can also use more sophisticated masking strategies like shown here in the middle, blind channel masking. And here basically we show to the model one full image, in this case the lower resolution strip map image acquired from the west, and then we ask it to reconstruct the other image, in this case the spotlight image acquired from the east. And of course this is a very hard pretext task for the model, but due to the acquisition parameters the model is shown, it has at least some rough idea what it's supposed to do. And then also a combination of the different masking strategies leads to a really powerful pre-training that allows us to create a high capacity model even with less labels. And now let's look at some results. This is the reference, the gold standard LiDAR-based digital surface model acquired from the Berlin Surveying Administration. So this is what you always want, and of course you can only achieve it if you do airborne laser scanning, but this is the target, let's say. This is the SAR image acquired by TerraSAR X in high resolution spotlight mode. Again, of course, Berlin, same scene. And this is what the Tandem X mission, if you know it, is capable of producing out of the box. And as you might know, the Tandem X mission is the German add-on mission to the TerraSAR X mission, which is designed to do a global digital surface model by means of standard SAR interferometry. So this is not deep learning based. It's really an old school stereo measurement principle that exploits the coherence between the images and the phase values. And then the output is a digital surface model at 12-meter resolution. This is the standard, so to speak. Yeah, what you can get right now with standard technology. And this is what our SAR to height SAR former can give you if you put in a single SAR intensity image. So for Tandem X, they needed two twin satellites, which is very costly, and they needed to fly these twin satellites a couple of years in a very complicated helix formation to get the result I've shown on the slide earlier. And this is what you can get if you have only one satellite, but our method. And if you add a second image, because I told you the SAR former can generally accept also n input images, and if we make n equal to 2, then we see that the buildings appear a bit more regularized, so even sharper in their outlines, and there are some more details. For example, if you look down here, it's the so-called Siegessäule. It's like the English word a monument. Which is not visible in the one image reconstruction, but becomes visible in the 2 image reconstruction. So we have a bit more details and a bit higher reconstruction quality. And then if we use the also predicted building footprint mask, which also comes just from the single intensity images, and we filter out everything that's not building related, then we basically end up with a level of detail 1, or maybe even close to level of detail 2 3D city model already. Of course, we wanted to also know whether this works for for missions where we have less images, for the whole new space things, where there's some cross mission or cross sensor generalization. So we have only very few images of ISI and not so many of Capella. Of course, we have many of Umbra, but you see that you can hardly see any difference. For all of those missions, we get similarly reasonable results. So the generalization capability is quite high just because of the self-supervised pre-training and the acquisition parameter encoding module. We also tried places that are not strongly represented in our training set. So here, this is Agadir in Morocco, more from the, let's say, global south, which is a bit underrepresented in our training set. A strip map image at that, which are also not so frequent as the spotlight images. And also here you see by predicting height map and building footprint mask, we can get a very nice map of the individual buildings and their heights in this area of Agadir. So to conclude also this example, integration of relevant acquisition parameters into deep neural networks helps the model to generalize better to unseen data. And this holds even more so if you use self-supervised pre-training. And of course, we are continuing this line of work, and we will in the future also consider other relevant sensor parameters, for example, wavelength, which could also provide the basis for an actual SAR foundation model. So something that goes beyond merely using Sentinel-1 images, for example. And this already brings me to the summary and conclusion of my talk. I wanted to show you today that processing SAR data with deep learning is really not the same as processing optical imagery, but the black box use of deep neural networks will likely not provide optimal results. So I want to suggest that you need to pair SAR expertise with deep neural networks to offer innovative solutions. And if you're interested in that topic, I can only recommend to you our newly published book. I edited it together with my dear colleague Ronny Hensch from DLR, from the German Aerospace Center. And it basically covers all the common topics in synthetic aperture remote sensing and how you can apply deep learning or specifically tailored deep learning solution to it. And I think I've shown two of them today, namely hybrid models, which combine SAR-specific physical models in neural networks, but also parameter-aware or sensor-aware deep neural network approaches. And especially if we pair this stuff with self-supervised learning, they can be a very nice basis for further developments and other downstream tasks, maybe even in the future an actual foundation model. And with that, I want to thank you for your attention. And I also want to mention that I'm currently looking for international incoming postdocs because I'm capable of providing one more Humboldt postdoc fellowship. There's a very prestigious German fellowship program. You can come to Germany for 6 to 24 months, only if you have never worked in Germany so far. And you will earn around 3,000 euros per month after taxes, which I believe is quite nice. And you will get plenty of additional financial support, including travel to and from Germany, mobility in Germany, health insurance, and some support for the project. So if you know anybody who could be interested in that, please tell them, spread the word, and help me finding somebody who I can give this nice scholarship to. Thank you for your attention.